Good morning and welcome to the next edition of Tech 259. In this video, I'm going to review problem set number 3. And in the next video, we're going to start talking about the first couple of laws of thermodynamics. So we'll get there in a little bit, but first let's go ahead and review problem set number 3. So I'm going to switch over to the document camera. All right, here is problem set number 3. And if you step back for a minute and take a look at these three problems, it's kind of sequential. It kind of makes sense, the order in which they go. Because we've got this fixed amount of water. We've got 2 liters of water. And we know that 1 liter of water has a mass of 1 kilogram. So 2 liters of water has a mass of 2 kilograms. We're going to have to use that. So we've got this certain amount of water. And in the first problem, we're increasing the temperature of that liquid water from 20 degrees Celsius to 80 degrees Celsius. And in the next problem, we're going to turn that 80 degrees Celsius water into superheated steam, which means steam that is above the boiling temperature, at 120 degrees Celsius. Obviously, that's above the boiling temperature, as long as we're at sea level at atmospheric pressure. So we've got this superheated steam at 120 degrees Celsius, and then we're going to increase the energy content of the steam by adding some more heat energy to that steam. The only difference in number 3, I changed it just a little bit because here we said that it's at constant pressure, but here in number 3, I said that it's a fixed or constant volume. So it's not quite the exact same situation as we had in the first 2 problems, but it's not that much different. So this kind of makes sense to go in order here. So let's start with number 1. We've got some liquid water, and we want to increase the temperature of 2 kilograms of water. It's in an open beaker, which tells us that it's at atmospheric pressure and a constant pressure. And we're changing it from 20 degrees Celsius to 80 degrees Celsius. So the first question here is this sensible heat or is this latent heat? And it should be fairly obvious that we are not exceeding the boiling temperature, and so this is just going to be sensible heat. So our equation for adding sensible heat is just Q equals MCAT. Q, heat additions, equals the mass times the specific heat capacity. In this case, it doesn't matter whether we're using C sub P or C sub V because it's a liquid. And so they're the same. C sub P equals C sub V for a liquid times the change in temperature. Right, so yeah, I said here, it's a liquid, therefore it's incompressible, and that's why C sub P, the specific heat capacity at constant pressure, equals C sub V, the specific heat capacity at constant volume. All right, so we just plug the numbers in here. We've got our mass, 2 kilograms, our specific heat capacity, that was given in the problem right there. And then we plug in our delta T. So our delta T is T2 minus T1, 80 degrees Celsius minus 20 degrees Celsius, which is 60 degrees Celsius. So you plug in all your numbers and then check out your units here. You got kilograms in the numerator here, kilograms in the denominator here, so those cancel out. And you've got degrees Celsius in the denominator here and in the numerator here, so those cancel out. And your only units left are kilojoules, which is good because Q is a unit of thermal energy, and a unit of energy is the joule or the kilojoule. So our answer is 502.3 kilojoules. Number 2 is probably the one that requires the most calculation. We've got this 2 kilograms of water at 80 degrees Celsius now from number 1, and we want to turn that into superheated steam at 120 degrees Celsius. All right, and we're told that it occurs at constant pressure, so we know which value of specific heat capacity we need to use for the steam. And we're given these parameters. We have the specific heat capacity of water, which is incompressible, so C sub P equals C sub V. We've got the specific latent heat of vaporization for water, turning into steam. And then we've also got the specific heat capacities of steam at constant pressure or at constant volume. So it's at constant pressure, so we need to use this one. All right, so there's going to be 3 parts here, right? Because we've got 2 sensible heat additions. First, we got the sensible heat addition of the water to get it from 80 degrees Celsius up to 100 degrees Celsius, the boiling temperature. Then we've got a latent heat addition because we got to boil that water. So that's just turning water at 100 degrees Celsius into steam at 100 degrees Celsius. And then we have the second sensible heat addition to get that steam at 100 degrees Celsius up to steam at 120 degrees Celsius. So there's going to be three calculations here, three different heat additions. First, we got our water, where we're going from 80 degrees Celsius to 100 degrees Celsius, and that's just sensible heat. So we use Q equals MCAT, where that's our M, that's our specific heat capacity, C of water, C sub P equals C sub V, remember. And then that is our delta T, T2 minus T1, 100 degrees Celsius minus 80 degrees Celsius is 20 degrees Celsius. Notice how our units cancel out, kilograms cancels out, degrees Celsius cancels out, and we are left with 167.4 kilojoules to get our water at 80 degrees Celsius up to water at 100 degrees Celsius. Then we have to turn that 100 degrees Celsius water into 100 degrees Celsius steam. So that is a latent heat addition. So we have this equation, the heat is equal to the mass times the specific latent heat. And so we have our mass at 2 kilograms and our specific latent heat at 2,265 kilojoules per kilogram. So kilograms cancels out, and we're left with 4,530 kilojoules to turn that 100 degrees Celsius water into 100 degrees Celsius steam. And then the last part is, once again, sensible heat. We've got steam now, and we want to turn it from 100 degrees Celsius steam into 120 degrees Celsius steam. So we're not changing phases, so this is just sensible heat again, a sensible heat addition. So we use MCAT, Q equals MC delta T. You just got to be careful which specific heat capacity you use now, because now it's a gas. So now we have to know whether it's at constant pressure or at constant volume. And this problem tells us that it's at constant pressure. Right? It told us it's at constant pressure. So we have to use C sub P, which is 1.97 kilojoules per kilogram degrees Celsius. So we plug those numbers in, 2 kilograms times 1.97 kilojoules per kilogram degrees Celsius, times delta T. T2 minus T1 is 120 degrees Celsius minus 100 degrees Celsius, which gives us 20 degrees Celsius. Our units cancel out, and we're left with 78.8 kilojoules to get us from 100 degrees Celsius steam to 120 degrees Celsius steam. So now we have to add these all together, because if we want to get from point 1, 80 degrees Celsius water, up to 120 degrees Celsius steam, we need to go through each of these separate steps. So we just add them all together. This value plus this value plus this value gives us 4,776.2 kilojoules. So I want to just step back for just a quick second and look at how much energy it took to get from 80 degrees Celsius water to 120 degrees Celsius steam. That is a lot of energy. Check that out in comparison to the answer to part 1. In part 1, we were actually increasing the temperature more. We were taking water at 20 degrees Celsius, cold water, and turning it into hot water at 80 degrees Celsius. And that only took 502 kilojoules of thermal energy. But now we're only changing the temperature really by 40 degrees Celsius, from 80 degrees Celsius liquid water to 120 degrees Celsius superheated steam. But look how much energy that took in comparison to the answer to part 1. And look at how much of that was actually in step 2. So the conclusion really we should draw from this is that it takes a lot of energy to turn water into steam, or to boil a liquid. It takes a lot of energy. So what you can also say from looking at that is that steam, when you've got steam, it contains a lot more energy than hot water. So it's a lot more energetic than water is. All right, so now we got this 120 degrees Celsius steam. And the question for number 3 is just a little bit different. It's not really asking about Q, it's asking about the total increase in enthalpy, right? Which is like the total energy content. But it's a gas now, steam is a gas. And so we have to worry about the pressure and the volume of this gas as well, because steam and gases are not incompressible. So we have to worry about the pressure and the volume as well. So what do we got? We got 2 kilograms of steam where we've added 50 kilojoules of heat energy Q, but it's constrained to a fixed volume. And we have the pressure, of course, then since it's constrained to a fixed volume and we're adding thermal energy, we know the pressure is going to go up. So the pressure increases from 101.3 kilopascal, that's 101,300 Pascal, which is the standard unit, to 120,000 Pascal. What is the total increase in enthalpy? And we're given the volume here. All right, so, and we have a few hints. We're given the definition of a joule. We have a few different definitions. This one right here might come in handy. 1 joule is equal to 1 Pascal times a meter cubed. And we have our specific heat capacities for steam. Which one are we going to use? Well, it says it's at constant volume right here. So we're going to use this one, C sub V. All right, so it's asking about total increase in enthalpy. So we have an equation for that. We have delta H is our enthalpy equals the change in U, delta U, which is our internal energy, which is made up of Q and W. Q is the heat energy, and W is the work, if it does any work added or subtracted from it. And then we add delta U plus delta PV, where P is pressure and V is volume. So this is the change in pressure and volume. All right, so one thing to note here, when we're looking at the delta U, change in internal energy, it's at a constant volume. And if it's at a constant volume, then it's not expanding and it's not contracting. So there's no movement, there's no displacement, there's no movement. And so therefore the work is going to equal 0. It's not having any work done on it. That would be like if we were compressing it. And it's not doing any work. That'd be like if it was expanding and pushing a piston in a cylinder or something like that. So it's not doing either one of those. So the work in this case equals 0 because it's a fixed volume. But we are told that the heat added, we do have heat added, Q, of 50 kilojoules. So our delta U is just 50 kilojoules. And note that we actually could calculate delta T if we wanted to. Because we have an equation for that. This is just sensible heat at a constant volume. We have an equation for that. We could use Q equals MCAT as long as we used C sub V, and we could find what delta T is, but there's no reason to. We don't need to, so I'm not going to in this problem. But you certainly could find delta T for this problem here. But all we really need from this step is that delta U, change in internal energy, equals 50 kilojoules. That takes care of half of our equation for change in enthalpy. The next half is the change in pressure times volume. So the change in pressure times volume is PV2, pressure times volume at time 2, minus PV1, the pressure times the volume at time 1. All right, so we have all this information. We are told the pressure at time 2 and the pressure at time 1, and we're told it's at a constant volume of 1.5 meter cubed. So that's the volume at time 1 and time 2. So we take the pressure in pascals, because that's the base unit, times the volume at time 2, minus the pressure in pascals times the volume at time 1, and you end up with 180,000 pascals times meter cubed, which remember is a joule. That's at time 2, minus 151,950 pascals times meters cubed, which is also a joule. And you subtract that, and you end up with 28.1 kilojoules. So that is the second half of our change in enthalpy equation. So now all it's left to do is add these two together. We have delta U, we have delta PV. Delta U came from right here, it's 50 kilojoules. Delta PV came from right here, it was 28.1 kilojoules. So our change in enthalpy, kind of like the change in the total energy content of that system, is 78.1 kilojoules. All right, so as always, let me know if you have any questions about those. In the next video, we're going to start talking about a couple of the laws of thermodynamics. So I'll see you in the next video.